So I'm taking care of building and development of ELI X-ray spectroscopy end station. And today's talk, I would like to start with a short story. So last year I was at a conference in San Francisco. I had a talk there, and this talk was scheduled for the very beginning of a session. And so just before the session, a chairman came to me and asked me, Anna, hello, how are you? He was, of course, very nice. How was your trip? And then he asked, Anna, what is ELI? So today I would like to use the opportunity, and in the first part of my talk, I would like to speak about what is ELI project and to give you an idea what is ELI Beamlines. And in the second part of my project, I will focus on status and perspective of ELI X-ray spectroscopy end station, and this part will be focused on the instrumentation. All right. As you might remember, in 2018, Gerard Morrow, together with his PhD student Donna Strickland, were awarded the Nobel Prize for discovery of chirped pulse amplification technique. The idea of the technique is very simple and elegant. If one has a weak laser pulse, this pulse can be stretched, then amplified and compressed back. And in this way, one can obtain a very intense, compressed, amplified short pulse. So this idea and this technique served as a basis for the ELI initiative, being a pan-European project, including 3 complementary facilities that are all based on extremely intense laser systems to perform laser science, drive secondary sources, and use this radiation at corresponding end stations. Here in the pictures, you can see Gerard Morrow, who visited the ELI Beamlines facility when it was in a building stage. And then later on, Gerard Morrow also visited the grand opening of ELI in 2015. So ELI stands for Extreme Light Infrastructure. The project includes 3 specialized facilities. The first one is ELI Beamlines in Dolní Břežany, Czech Republic. It is specialized on high energy beams, and at this facility I am working. Another one is ELI Attosecond or ELI Alps in Szeged, Hungary. And the third one is ELI Nuclear Physics in Măgurele, Romania. Based on the achieved progress during the parallel implementation phase, ELI Beamlines and ELI Alps were approved to enter the next phase, which is ERIC Consortium. And we, of course, all strongly hope that in future, Romania will join the consortium as well. Here you can see a research campus in Dolní Břežany. So this is HiLaser. This is a neighboring, also laser-based facility, and this is ELI itself. The facility houses 300 employees and has the office building, laboratory building, and a laser building. Here you can see a layout of the laser building. And as you can see on the ground floor, laser teams take care of development of 4 different intense lasers. The most intense one will have a peak power of 10 petawatt. And then using beam transport, the laser beams are delivered downstairs to the basement where we have experimental halls. I'm working in E1 experimental hall focused on material and biomolecular applications and using L1 laser. Another name of this laser is Electra laser. Here you can see the main parameters of an L1 laser. The aimed pulse energy is 100 millijoules, pulse length of 20 femtoseconds, and repetition rate of 1 kilohertz. So here you can see the most updated picture from E1 experimental hall. Here you can see our state of the art. The beauty of this hall is that complementary end stations, complementary techniques are located in close vicinity to each other. So one can perform a complementary study here in the experimental hall. As I have told already, Allegra is delivered through the beam transport from the upstairs to the hall. The beam is transported in vacuum system, and then it goes to the secondary sources, which are HEG, high harmonic generation, and XAS plasma X-ray sources. Then the emitted radiation is used at the end stations. One of them is MAC station, which is focused on atomic and molecular science and coherent imaging. There are X-ray spectroscopy and X-ray diffractometry end stations. And there is a separate SRS station for simulated Raman spectroscopy for optical spectroscopy. In the hall, we use support lasers. We have had Astrella laser installed at the SRS station, and later on we have got also Legend and Hydra lasers, which are installed here on the laser table. These are the most new lasers. They have come to us in the beginning of this year, and we have already ran similar few experiments with these sources. As you might have already understood, we are running our X-ray science here in this blue hutch, shielded from X-rays. And this might be time for our first questions.
Thank you. That's great. I'll keep an eye on chat, but let me ask a question or two myself. One of the interesting features of ELI is the use of the laser light for so many different reasons. Are there other facilities that also have such high-powered lasers being used, not just for plasma physics, but also for material science and photochemistry and so on?
Well, first of all, I would like to say that at ELI facilities, the lasers will be used also, not only for driving secondary sources, but for other purposes as well. Another facility is basically the neighboring one, which I was speaking about in the very beginning. This is Highleys. They also have intense lasers that they are using for laser science.
Okay. And I was trying to compare and contrast, for example, with NIF, with National Ignition Facility, that does have some astrophysics projects, though on the plasma side. Are there, I just don't know the laser community that well. Are there other large laser facilities that support material science work in this way?
You know, to be honest, right now, I can't remember.
Okay.
Facilities because say in Europe, at least we usually say that ELI project with the 3 pillars is a unique one with the most advanced lasers in Europe. I might be missing something around the world. Okay,
that's fine. That's a great start to the talk, and seeing no other questions, you should continue. Thank you. Wait a minute, we have a question. Is there any tunability of the laser in terms of output wavelength?
Well, one could use, say, BBO crystals and LBO crystals, but say as we get the lasers, they have 824 nanometers, if I'm not mistaken. And then, yeah, one could in principle use different techniques to tune those lasers. Like for instance, at the SRS station, we have BBO crystals, and we can tune the frequencies of the lasers, and we can get different energies as well. Like for instance, this will be used, we have already established beam transport from the SRS station to the X-ray hutch, and this beam transport will be used for delivering pump beams to the X-ray hutch, and we will be using not only this 824 nanometers, but other wavelengths as well. Let's say, like for instance, 412 and similar.
Okay.
Like
excellent. Thank you. You should continue now. Thank you.
All right, let's move on. So on this slide, you see a layout of the TREX station. TREX stands for Time Results Experiments with X-rays. And this is what is contained in the X-ray hutch. Here you can see, say, a location for an X-ray source, and basically we will be using alternative X-ray sources, and also two end stations, X-ray diffractometry and X-ray spectroscopy. Today we will be speaking about X-ray spectroscopy. For the X-ray spectroscopy end station, we will use a few alternative X-ray sources. The first one is a continuous wave conventional X-ray tube. As this is a continuous wave source, it will be used for steady state studies. It has a molybdenum anode, and it's already running there. In the X-ray hatch, another source is a metal jet plasma X-ray source. This source is currently under development, which has turned out to be a pretty challenging process. So about this source, I will speak in detail a bit later on, but it will deliver pulsed radiation, and so it can be used for time results studies. Another pulsed radiation source will be a copper tape source. This type of sources has already proven its stable work and reliability, as it's ran at few different facilities. I'm pretty sure one copper tape source is run in Göttingen, and another one, if I'm not mistaken, is in Berlin. The copper tape source has been already contracted and is expected to be delivered to ELI Beamlines in the end of 2020. And another pulsed radiation source is wire jet plasma X-ray source. This source was adapted to the ELI laser intensities by our collaborator Jens Ulik, who is, I think that he's actually here in this session today present. Jens has adopted the wire jet plasma X-ray source for L1 intensities, and about this source I will be also speaking a bit later on, but this source has been already commissioned, and it has performed some very initial results last year. All right, here you can see a scheme of the metal jet plasma X-ray source. This is source driven by laser, and the laser is delivered in vacuum through the beam transport onto a mirror. This mirror reflects the laser onto a focusing parabola, and the focusing parabola focuses X-rays into the X-ray core. In general, high intensity of focused femtosecond laser pulses would damage a metallic target. Therefore, in order to provide continuous X-ray generation, the target needs to be continuously refreshed so that every pulse interacts with a fresh target. That is why in the X-ray core, liquid metal jet is circulated in a closed loop. So it's basically continuously renewing alloy of metals. In the X-ray core, indium and bismuth are kept at a certain temperature. If I'm not mistaken, it's something around 70 up to 80 degrees Celsius. And the radiation that will be radiated by the source will have characteristic lines at 3.3 kiloelectron volts, 10.8 kiloelectron volts, 24.2 kiloelectron volts, 77.1 kiloelectron volts, as well as Bremsstrahlung, which will be nicely useful for the X-ray spectroscopy studies. In the next slide, you can see a scheme of X-ray spectroscopy, which at ELI is realized in von Hammer's geometry. In this particular picture, you see a wire jet source, but in general, any of the alternative sources can be here. The source irradiates X-rays that penetrate through a sample. Here you can see the X-ray spectroscopy in the absorption geometry. And so the X-rays that are transmitted through the sample go onto a focusing crystal, and the focusing crystal focuses and resolves the photons onto a detector. In our case, this is a CCD detector. So in this way, we can by the location of the arrival of photons, resolve the photons by their energy. According to the TREX law, one can look at the material of the sample, and the energy of the characteristic lines of the sample predetermines the angle theta. Just a few words about the CCD that we are using. Our CCD is from under company, and in a usual CCD, let's say, a sensor is located relatively deep inside the camera, which means that if you look at the geometry, you understand that the housing of the CCD can create some kind of a shadow. In this way, a certain part of the sensor is not available for the measurements. It will be just dark. So in our case, we asked Under to customize the CCD in a way that the chip is located very close to the beryllium window. It's actually like few millimeters. So that the incident angle restriction is actually the sensor size, not the camera part. And also actually we have here a beryllium window, which is a little bit enlarged in respect to a standard CCD. Here I'd like to show you a current status of the X-ray spectroscopy end station with molybdenum anode X-ray tube. We have an X-ray tube from XAS. It has a molybdenum anode. It has a polycapillary which focuses the rays onto a sample. Currently, we're working mostly with robust samples. Then the X-rays go onto a focusing band crystal, and the crystal focuses the X-rays onto the CCD detector. The CCD detector is mounted on a motorized stage so that we can scan along the energy axis. On the next slide, you can see current status of the X-ray spectroscopy and station using the water jet plasma X-ray source. So this is now a pulsed radiation source. As I have told already, the beam is delivered to the hatch and consequently to the source in vacuum. So here is a vacuum chamber, here is a vacuum window, which is specifically anti-reflection coated. There is an iris, there is an adjustable beam splitter, and through all this construction, the beam is directed onto a focusing parabola. Unfortunately, in this picture, you don't see the parabola itself, you see on the optomechanics, but trust me, the parabola is there. So the parabola focuses the beam onto a water jet that is circulated in a vacuum chamber. Basically, the beauty of this source is that it's, as you see, it's a very compact source. Here you can see water inlet, water outlet, and the focused laser creates plasma, and plasma interacts with water, creating X-rays in 4 pi. Now in this wall, there is an X-ray slit that kind of cuts out a part of this 4 pi emission, and then we can use this beam later on in the experiment. So here is a sample. The whole geometry is aligned for an iron sample. Here is again a focusing crystal and a CCD detector. On the left slide of on the left panel of this slide, you can see a nice experimental result, which was published in 2015 in this nice paper. This is experimental gain of X-ray spectra produced by a previous modification of the water jet source. And what you can see here is a gain of photons when the water jet source was driven by different lasers, well, basically with different pulse energy of laser. And as you can see here, with the increase of pulse energy of a driving laser, you gain non-linearly more photons. As I like to say, every millijoule matters in this process. On the right panel, you can see X-ray spectrum generated by the water jet source using Astrella laser. This result is achieved at ELI Beamlines. We used an Uptech X-ray diode for detection of these X-rays. And what we can see is basically that the shape of the spectrum replicates the shape of the spectrum obtained in this publication. And on the bottom, what you can see is the most fresh result. Very recently, we ran an experiment using a legend laser, which is more intense than Astrella laser. And what we have obtained is this peak, which is a photon peak of photons generated by the Voyager source. And the height of this peak is around 1.2 millivolts. And one can compare it with 0.65 millivolts when generated by the Astrella laser. All right. So these are the results that we gained with the Voyager plasma X-ray source at ELI Beamlines in autumn last year. This is X-ray emission spectrum, and this is the iron K alpha line. And on the right side is actually a very interesting result. So when the Voyager source was delivered to ELI, we asked ourselves a question, whether or not the Voyager source can be used with our von Hamos spectrometer in our setup. Simply because the question was if the brilliance of the source is enough for the von Hamos spectrometer. So usually when running a Voyager source, at laboratories, people use microcalorimeter sensors. As far as I remember, a talk about a transition edge sensor was given already within the framework of this journal club. Usually the Voyager source is used, for instance, with test detector. The advantage of the test detector is that it resolves the photons by energy on itself, on its own. So one doesn't need a spectrometer. In the von Hamos, while the von Hamos delivers a higher energy resolution, but photons have to travel way longer distance. And also we lose certain amount of photons by the size of the focusing crystal, because currently we are using only one single focusing crystal. So what you can see here is actually the answer to that question. Basically, these frames are 30 minutes acquisitions, and these are cuts, these are regions of interest. Because in general, what one sees during the experiment is a black screen, which is the sensor of the CCD, and then white spots are photons, and then one sees the X-ray absorption spectroscopy signal as photons that have been transmitted and the photons that have appeared as a result of the interactions inside the material, and then the absorption edge, and then the photons that were taken by them or absorbed by a sample. Of course, one would aim at better focusing, so we are working on it, and also this particular result was achieved by the Astrella laser, which is less intense. Currently we have the legend laser, so we will have a higher number of photons, but this proves the principle. It is possible to gain XAS information with a combination of the Voyager source and von Hamos spectrometer. I think it might be time for questions.
Yes, thank you. If you can just go back one slide.
This one or the
start. It's great to see photons. Can you show us a Zane spectrum or something by processing of the camera images?
Actually, no, not simply because looking at this spectra, well, I mean, I have those process data, but I don't have them right now here in the presentation, unfortunately. But what I can say is that, say, for good and reliable signal, and for, you know, getting some data out of this, one requires a better focusing.
I see.
In that case, we were running out of time, very simply because this was the end of the beam time and everything worked. So we decided to, gain the signal as we could gain it, and then work further to get data that would be basically reasonable to show and to process.
Okay. There's some questions about spot sizes we want to understand. So for the water jet, for example, first, what's the size of the laser spot on the water jet and consequently the size of the X-ray spot?
I would be here speaking rather about the plasma spot, so which is, let's say, a little bit bigger than the focal spot itself, but we are speaking here about some tens of micrometers, the plasma spot on the water jet. And the water jet itself at ELI is something around 300 micrometers. This is a cylindrical shaped jet, and it has the thickness or the diameter of around 300 micrometers.
Okay. And so if you go back to the experimental configuration that shows the rays going from the source to the optic. Yeah, that, excellent. So you have a polycapillary. What's your refocal spot size?
So the refocal spot size is something around 100 micrometers.
Okay. And so you would be able, of course, to branch off either the main laser or use a secondary laser to do pump probe on that 100 micron spot, yes?
Exactly. So it's not hard to focus some fraction of the same laser. So basically we use a beam splitter in beam transport, and a certain part of the beam goes to drive the laser, another part of the beam goes to probe the beam, or to say in case of optical pump, X-ray probe, to pump the beam. Yes, we can use different lenses to focus to a bigger size onto a sample.
Okay. Jacinto, you had a question?
Yeah. Anna, do you know if we would gain anything by having a flat jet instead of the cylindrical jet?
Say again, please.
If we could have a flat jet instead of a cylindrical jet, would you gain anything?
You mean in the water jet source?
Yes.
Well, what I know is actually that we have to tangentially fire into the water jet. Actually, well, here is Jens, who can perhaps answer this question better, but as far as I understand, well, it's actually a very good question. Well, definitely there will be some X-rays generated. The question is, what are the advantages and disadvantages of this system then?
If I might hop in there. In short, one of the key points of the jet is that the water is simple to handle, and if you handle a focus of a few microns, then making a flat stable water jet is very difficult. So it's actually better with the round jet because you get a much more stable jet in this configuration.
Yeah, perhaps here I might add that we are working on development of flat jets for sample delivery systems. And in the framework of what Jens has said, that's true that it's not so easy to gain a stable spot. And usually a stable spot would be somewhere in the middle of, say it would be a bit closer to the output of water, and in terms of the width, the stable area would be in the middle, and so the X-rays would have to, first go through some layer of water, and then to go onto an X-ray slit, because we don't place the X-ray output slit behind the laser direction, simply because otherwise we would have to, burn, say, for instance, polycapillary.
Okay.
And I was saying that there has been, of course, people developing white light for optical with water jets with which are like flat and but I guess they would be not very stable for the X-rays.
All right, let's move on. Yulia, you had a question about the general science goals. You're muted, Yulia. There you are.
Sorry. So basically, my question is, where do you see your unique niche? Yeah, because it's obviously here you're competing with free electron lasers, which are monochromatic, much brighter. So what is the unique scientific questions? What is the driving directions, or how to say, driving scientific goals for those developments?
Well, that's a great question. Thank you, Yulia, for this question. The main advantage of, I would say, E1 whole and maybe the whole ELI Beamlines facility itself is that we have complementary techniques that are located very close to each other. So you have seen in one of the previous slides that a few different end stations are located close to each other. So one can make really very complementary, very full study of their samples, simply coming from the, say, X-ray hush to the SRS station and already gaining optical information on the sample, and then going looking, say, closer into details with the X-ray spectroscopy, simply because optical spectroscopy delivers, of course, lots of information, but it's, say, not then with X-ray spectroscopy, you can gain more detailed information on your sample. For instance, I think last year there was a publication from Maria Naumova when they made a very big complementary study, and they had to use, if I'm not mistaken, either 3 or 4 facilities I counted there in this study or in this publication. They had to really go to ELI Beamlines, then to Petra, to DESI, then they had to go to another facility in Germany to gain the information that will be possible to gain only within ELI Beamlines. So, you know, the accessibility of user facilities is pretty much limited. This is pretty problematic to get at least one beam time. And speaking about a few different beam times, when one has to gain complementary information on a sample, this becomes a really challenging task and very time-consuming task as well.
Okay, thank you. Go ahead, Jacinto.
I mean, there is also very practical things about the ELI that first is that you have perfect synchronization, so there is no need for time tool, which is an absolute nightmare at the free electron lasers. So they can give you as much as they want 5 femtoseconds, but they cannot get a time tool to work better than 500 femtoseconds. From day one, ELI will deliver at least 300 femtosecond resolution without any problem. Then the other thing is that you can use a lot more exotic pump schemes. You can use, for example, pulse shaping, which is impossible to do at the free electron laser. And then I would say even probably more relevant is that you have extremely low sample damage compared with the free electron laser. So I don't think we should see ELI really as a direct competitor for XFEL, but actually as something that suppresses a lot of the problems that XFEL will always struggle to get into.
A very good point. Thank you. Ricardo Rice, you have a question?
So I would like to know if it's possible to add for this setup some sample environments like low temperatures, high pressure, or if combined with lasers doing like shockwave compressions or something like this. Are you planning to do something like this?
Yes, thank you for the question. So with the sample environments, we are definitely going to develop into various different sample delivery systems. And for instance, at the diffractometry station, there is already present a cooling cryostat for samples. Like for example, with X-ray spectroscopy, simply because the project has been started slightly later, we are not yet at that phase, but definitely we are looking into this direction and we are planning such things. Yes.
One last question, I'll paraphrase. Can you explain why it's important to use the polycapillary, which of course has limited efficiency, rather than just taking the light from the water jet X-ray source straight to the analyzer?
Yes, that's a very good question. So the plasma X-ray sources basically generate X-rays and emit them in 4pi. And then, yes, we can, and we basically have an X-ray window, kind of an X-ray slit that we can use as a shaper for the beam. But still the beam will be a little bit divergent, and then of course, depending on where you place your sample, you will have already not that much focused beam, which means you will have not so many photons. As I have told already, we were questioning ourselves whether or not it would be possible to use the water jet source in general with the von Hammer spectroscopy. That's because the brilliance is kind of limited, right? On the other hand, the result that I have shown you, this is exactly, it's gained without a polycapillary. That's a great point. But when we have a polycapillary, even though it slightly elongates a pulse, so instead of femtosecond pulse duration, we get picosecond pulse duration, but it kind of re-images the photons into a particular focal spot. And so in the particular focal spot, we simply have more photons. And in this way, we get more information in say, one second or 1 hour, right, within a time frame. And in this way, we simply cut our measurement time. On the other hand, for pump probe experiments, of course, it's important that the pump beam is slightly larger than the probe beam. And then the area, the size of the area of the interaction of X-rays with the samples starts mattering.
Yeah, I see. Yeah, so you need the small X-ray spot on the sample in order to be able to do pump probe. Very good.
Well, in general, of course, we could go a bit closer to the X-ray window, and I will show you later on that we are planning to do that. But let's say for certain experiments, you want to have a smaller spot, for certain not. This also depends on the size of your sample, because sometimes the samples can be also not very big, right?
Very good. Very good. Thank you. You should continue, please.
All right, let's move on. I think I stopped here. So, and now I want to tell you just a few words about the outlook, about the perspectives of the X-ray spectroscopy at ELI Beamlines. And one of them is a so-called X-box, which is an offline X-ray spectroscopy station. I'd like to say that when I started this branch of the development of the X-ray spectroscopy here, I was inspired by a setup of our colleagues in Warsaw who have a similar X-ray shielding station, and they perform their experiments at that setup. So in our case, the station, as you see it here, was designed by the company X-ray Protect. And it will have 4 openable doors so that one can access the setup easily from all 4 sides. The station will also have ventilation so that we can later on perform, say, experiments with gases, for instance, or with cooling samples with, for instance, liquid nitrogen. In the X-box, there will be mounted a breadboard. On the breadboard, there will be an X-ray tube. Basically, because we are going to use an X-ray tube at this station, we call it an offline X-box. And there will be, of course, the rest of the setup, the focusing crystal and the detector. Currently, we are also working on the interlock system, safety system of this station, and we very much hope that the station will be available for user experiments in the end of this year. So what I want to show you here is directly connected to the question about samples. Even though right now we're working with robust samples, we are planning to switch to liquid samples soon. In the very beginning, we were going to use a setup developed by my colleague Alessandra Picciotti during her PhD. But then we with Alessandra discovered that the previous iteration of the setup, about which you can read in this nice publication, was actually too big for this, I would say, peculiar shape of the vacuum chamber. That's why we have made another iteration of this liquid sample delivery system, which is now way more compact, and it nicely fits the station parameters. And now we can use it either with a polycapillary or without a polycapillary. As was already pointed out, we can use a slit as a shaper and to place the liquid sample as close to the output as possible. In this way, basically, we get rid of the polycapillary and we get rid of the pulse elongation of X-rays. The main advantage of this liquid sample delivery system is that it delivers flat sheets of sample. The thickness of the samples varies between 100 and 300 micrometers. And the liquid is tensioned between two guiding wires. In this way, we can use the system for liquid samples in various different options or variants. And here I'd like to show you our developments towards pump probe experiments. So beam transport from the optical spectroscopy end station was has been built already. So the beam could go either on the top or on the bottom, and it will be delivered to the X-ray hatch. In the X-ray hatch there is already installed beam transport so that the beam can be easily delivered to the sample of the spectroscopy end station. Another direction to move forward is a matrix of focusing crystals, because as I have told already, we are now using only one crystal for focusing, but later on we would like to have a matrix of crystals. In this way we will be catching more photons, which again decreases the experimental time, giving more useful counts at a time. And this system is expected to be commissioned around the beginning of 2021. And another branch is establishment of X-ray emission spectroscopy for complementary studies, and in this way we can gain in parallel information on occupied and on unoccupied states of a sample. Our facility is based on the principle of direct accessibility of people who are taking care of secondary sources or end stations. So here I show you a list of contacts in case of interest. These people are very open to discussions, any ideas of prospective experiments. They will help to find out the details of different setups at our facility and in our particular experimental hall, because these are people who are working mostly in E1 experimental hall. And they will readily and happily answer your questions and discuss any prospective measurements. Here is a picture from the ISIL conference, which was held at ELI. This conference went pretty successfully, and we had user meetings parallel to this conference. One of them was X-ray user meeting. In this year, the user meeting is scheduled for autumn, and I would like to ask you to check ELI Beamlines website for more details and more announcement. With this, I would like to thank you for your kind listening.
Excellent. Thank you, Anna. That was lovely. While we wait for people to put in a few more questions, I have a few. One is there any possibility that the water jet could be modified so there could be a second beam, that being the sample jet, much closer to the water jet so you could subtend a bigger angle?
Running a plasma X-ray source with a liquid jet, basically the one thing you suffer from is a debris.
Yes.
So this is basically the droplets of the material that is used as a jet. As far as I know, in case of Jens, for instance, he uses a smaller setup. But in that case, the lasers that are planned to be used are less intense. And so in our case, because we are going to use a very intense laser, we will have more intense droplets as well. And these droplets will block a little bit the windows. That's why, well, this is of course up to testing. As soon as we will be ready with this setup, we will be thinking of any other directions of upgrades of this setup. Again, this is about testing, because for instance with the metal jet plasma X-ray source, what I know from the developers of it is when they ran it for the first time, they had the jet in a very big vacuum chamber. So they did not really care of the droplets, because the droplets simply did not get to the windows, and they did not block the windows. In our case, also in the metal jet source development, this is a relatively big problem, simply because it's very compact, and so the windows get covered with debris from the jet.
I see. Okay, I understand. You had there's a question of can you just describe in rough terms what's the process to apply for beam time, or is it more experimental and one should contact the beamline scientist directly?
Yes, basically there are two main ways. So we have already had call 0, and now we are preparing call 1. It will be announced soon. And one way is basically to go through this call 1, through the official call, and to have some kind of a proposal, and this proposal will be evaluated by a panel of people who will be working with this experiment, and also the collaborators. And another way is basically also to directly ask the particular people whom list of contacts I have shown. It is also possible because we are currently also having many in-house beam times, and within this in-house beam times we could run different experiments. Yes.
Very good, thank you. One more question. If you go back to the slide that had the energy spectra for the spectrum generated by the liquid jet, I think it was. Yeah, that. What's the cause of the energy cutoff that one sees right about where your laser pointer is?
Here you mean, right?
Yes.
So yeah, basically the point is that this is generally branch-Strahlen radiation, right? And then simply with the higher the photon energies here are, the more intensity of the laser needs to be. So this is simply because, let's say, there is not enough energy for creation of photons, of many photons, let's say, of higher energies. So with, let's say, with a higher pulse energy of the driving laser, one can achieve this cutoff to be smoother, perhaps, and definitely at higher energies.